Thank you. Thank you, Anupma. All right, well, I just want to make sure that everybody can hear me while I'm up here talking. Today, I'm going to talk about how Alaska puts the remote in remote sensing. But I do want to take just a moment before we get going, and I think it's wonderful that the Triple Horns are here for this, because I too believe that our society should be scientifically literate, and I really appreciate you guys coming out this evening to listen to this talk. I'm not sure how much you know about remote sensing, but I'm hoping that you can learn a little bit here. But I truly believe that there's value in people from all walks of life, all industries, all parts of the world. Doesn't matter who you are, where you're from. Having some knowledge of science, especially in this day and age, is very important. It's important for decision making. It's important for you to know what's going on in the world. And from my perspective, I would like it if you have enough knowledge to be trustful of the science that's being presented to you by scientists. So that's, I strongly believe in this, and that's why I really appreciate these Science for Alaska series. But let's talk about remote sensing. So actually, you know, this is actually a remote sensing device, right? Because you don't have to get up. And I love this audience because I don't have to explain to you what it used to be like when you had to get up and turn, right? So I work at the university, and so there's sometimes I'm talking to an audience who's like, so was your remote control not working? It's like, yeah, it didn't exist. But this is a remote controlled device. But in Alaska, we also think about this kind of remote, right? And actually, in my discussion tonight, we're going to talk about this as well. Alaska is remote in many different ways. But from my perspective, as a scientist, this is what I think of as remote. So from me, most of the stuff that I look at and the things that I spend my day on are working with satellites that are out in space and circling the Earth. But what is remote sensing? What does that mean? Well, it's acquiring, processing, and interpreting images and data from aircraft and satellites. There's actually more to it, but I'm really going to focus on aircraft and satellites that record the interaction between matter and electromagnetic radiation. Clears it right up, right? So what does that mean? It means that remote sensing is observing from a distance. So just like your remote control device for your television or your remote car starter, you don't have to touch it to make something happen, right? And in our case, we're observing nature, and it's remote sensing from a distance. There's no physical contact with the object of study. So if we think about it in a really simple case, we can think about looking at a tree from different distances. If I'm standing below the tree and looking up, I can touch the tree, I can interact with it physically, I can look up and I can learn things about the tree. If I'm flying overhead in an aircraft, or if I send a drone over the top, I can learn things more about the forest because I can see a bigger area and it's a different perspective. So both are good things for scientists to do. Both give us different information. But what if I'm in a satellite? I'm looking at trees in these two images from the satellite. This is from Landsat. And there, if you notice the dates on the top, this is 2017, there's not that many days in between these. And look at how remarkably different they are. So the one on August 25th is before Irma, and the one closer to me is after Irma. It's a Category 5 storm that hit this Caribbean island, and it decimated the forest. So that's another way we can learn about the trees, but you need a satellite to do that. So Alaska is remote in other ways as well. I don't know if you can see this very well, but this is a NASA image. It's time-lapse, and it's the United States at night, right? So you can see, I think somebody left their porch light on in Fairbanks because you can see Fairbanks up there, but you see the difference. So we really are remote in many different ways. So remote sensing data can come from many different sources. So a lot of what I do, I'm going to see if I can do this without, oh, look at that. A lot of what I do is from spacecraft, some from aircraft, but we also have a lot of unmanned aerial vehicles. I sometimes forget and call them drones, but we have a lot of those at the university. And we also have some underwater autonomous vehicles that we can do data collections with. But you can also do remote sensing, a land-based observation of ocean currents. We do that as well. And then you can also sense from above ground things that are happening below ground. And all of this information needs to be gathered and handled in some way. And some of it is very complicated mathematically, but we're not going to talk about that tonight. So these, oh, look at that. I did do exactly what they told me not to, is turn and yell into the mic. So sorry about that. These are the antennas which we use to communicate with the satellites that are in space. So we'll talk about a little bit about both of those things. So when you're choosing how you're going to observe remotely, in a satellite situation, you can observe big swaths at a time. A lot of times the detail is not there because you don't have as much resolution, but you have a much bigger area. If you did use an airplane in the same area, see, there's my little airplane, and that's the information that airplane is gathering. So the swath is much smaller, but the detail is much greater. So you balance those two things out. As a scientist, you figure out what are you going to use. And sometimes, depending on the science, we do what's called telescoping. We'll start with the satellite, we'll figure out where we want to fly the plane, and then we fly the plane and we figure out where we're going to send the scientist. So it's a little bit of a telescoping down to figure out what we're doing. So we're using resources so that we don't just have scientists wandering in the woods. Although we do that too, I suppose. But we have a whole team of people at UAF's Geophysical Institute working on remote sensing in some way. Dr. Prakash, who introduced me, is a remote sensing scientist herself, as is her husband, Rudy, who's sitting next to her. So there's a whole team of people, scientists, engineers, technicians. We have a lot of students, undergraduate and graduate students. We also have a lot of support staff that are needed in order to help the projects keep going. And a lot of people see these big antennas. This is the one that's out in the woods. It's one of the two that you see out in the woods. And then one on top of the big tall building. You see these ASF antennas, but there's really more to the story. We are studying the Earth from a distance, but how are we doing that? Why are we doing that? But I want to start with where. So this is a bit of a pet peeve of mine. If you Google map of the United States, you get about 1,000 or so of these. Makes me crazy. So, and if I was just in DC, and I was literally stuck in DC, so I watched the news, and this is what they use. Alaska is not an island off the coast of California, and Hawaii is not in central Mexico. So this really bugs me. Location is important. It's important to what I do as a scientist, and it's important to NASA, so we'll talk about that. So this is wrong. This is worse. Where'd we go? We're not even there anymore. I'm like, God, Continental US, right? Don't ever let them tell you that they can't ship to you because you're not on the Continental US. Yeah, we are. We're on the continent. We're right up here. Now, if they mean contiguous US, then I get it. But so this is the continental US, and this is the image that I would like people to have of of the United States. Okay, I feel a little sorry for Hawaii because I think I cut them off. But this is what we need to think of, because we need to start understanding our space that we're in. But I can tell you that this is my worldview. So this is the polar view, and we use this a lot in our Arctic studies. This is the United States. So the United States is an Arctic nation because of us. And so this is an important viewpoint to have. This red line, I'm just gonna tell you, this red line is what's called an isotherm. So an isotherm is a line of constant temperature definition. So anything that's north of that line has the warmest month is less than, at or less than 10 degrees C, which is about 50 degrees Fahrenheit. So in July, the average temperature of July is colder than 50 degrees Fahrenheit at and north of that line. That's how we scientifically define Arctic. So it's an important distinction because a lot of times people just draw the Arctic Circle, but we miss a lot of Alaska that is actually Arctic climate, that if we do it that way. Or if we use political lines, the political lines, honestly, in my world, they mean nothing to me. So this is a scientific definition of the Arctic. And a lot of times we will notice that as scientists, we have more in common with the people around this red circle than we do with a lot of what happens in the lower 48 in terms of culture and climate, adaptability, and vulnerability. Right? So this is an important viewpoint. So at ASF, we love antennas. We love to talk to things in orbit in different ways. We have a bunch of different antennas. But really, what I want to focus on a little bit more is what we do with NASA. So we are very much integrated into NASA. As a matter of fact, I have a bunch of NASA visitors here this week. And these three large antennas, the big blue one that you see on the top of the Elvey building, and then you can see the tops of these just above the treetops, right, as you're driving down Geist Road. Be careful though, it's slick. Watch where you're going, but you can see those. I look at them every time I drive by. I love my antennas. So these are owned by NASA, operated by the Alaska Satellite Facility, and we're part of the Geophysical Institute at UAF. I always get, wait, what? NASA's here? Yeah, NASA's here. NASA is very much involved in the work that we do at the university. But a lot of what we do is Earth observations. And that's the other question I get a lot from people. Why is NASA studying the Earth? I thought they studied space. Well, guess what? We're in space. So we're one of the planets. We're kind of an ordinary planet around an ordinary star in a galaxy that is, you know, I mean, there's a lot out there. But it's a planet of convenience. We can study it because it's so close to us, right? So it's very easy to study the Earth compared to other planets, and there's a lot to learn. We don't know. There's a lot that we don't know about the Earth and about the systems that interact with each other. So we still have a lot to do. Okay, but why Fairbanks? Actually, Fairbanks is very important to NASA. And you can kind of see that if you go out into space a little bit. So we're going to talk a little bit about low Earth orbit. So you notice immediately that the low Earth orbit is more in a polar orbit, where these are equatorial, or towards the equatorial. So the geosynchronous orbit is probably the ones people hear about the most. Have you heard of geostationary, geosynchronous? So what that means is that the satellite is going in the same direction that the Earth is spinning, and so it's in sync with the Earth, geosynchronous, right? And if it's geostationary, it means that it looks like, to the person on Earth, it looks like it's hovering right there in space. It's because it's moving at the exact same speed in the same direction that you're doing, and you do that if you're in the equatorial plane. So this is where most of the communication satellites are. It's out there pretty far. It's 26,000 miles away. And the mid-Earth orbit, of course, we like to call these MEO, right? Because we make acronyms and then words out of every acronym. So the MEO, MEO. A MEO orbit is GPS, for example, are in those orbits. But What we're going to look at today and what Alaska Satellite Facility really focuses on is the LEO, the low Earth orbit. And a lot of that is because it is in the polar orbiting, which I will get to in a minute. This is just to give you a little bit of an idea. So here we are, the polar orbiting satellites. Those are the low Earth orbits. It's about 500 miles. The communication satellites are way up there. They're so far up I can't even really put them on the slide because I'm trying to do it to scale a little bit. And here is Alaska Airlines. Okay, so when you think you're really high in the air when you're flying, yeah, you're not. So this is Alaska Airlines. They fly, it's about 6.6 miles is about what you fly when you're on an airliner. And the answer to the question, will we fly through the aurora, is no. You'll fly under it, unless you get a ride on the space shuttle. Then you're above it. But that kind of gives you a relative feel for the height. So let's talk about the polar orbit here. I'm hoping this will work. I love it when things work. Okay, so I want you to look at the poles versus the equator as this polar orbiting satellite goes around and is taking pictures. So you notice how it fills in much faster down at the poles, and if you could see the other pole, you could see that as well. And that there's much more space open in the equatorial region, right? So it's like a ball of yarn. As you're going around, it precesses around, and you can see you're over the poles more than you're over the rest of the Earth, right? Well, why is that important? It's because when you live in Fairbanks, Alaska, yay us, this is what you get to see. So this is kind of from the other point of view. Now, okay, really, Nettie? Did you guys enjoy those slides? Because that was, I got excited. So, okay, so when you're on, maybe I shouldn't use this one. Do you see the light circle, right? That light circle, that is the ground mapping of what those big antennas are, where they can see. So when a satellite is coming around and crossing that circle, we can either listen to it or talk to it, or we can do both, right? So that's a lot. So you think about the space that we cover, it's a lot. And then if I just show you one slide at a time, then if you think about those are the ground tracks of that a satellite as it orbits, and you notice, if I push this very carefully, that they group around the poles, just like a ball of yarn, right? So we see about 11 of these a day, whereas people in Washington, D.C. or in that area see about 1 or maybe 2 a day. So we are much better at having a ground station with the antennas here than we would be there. So one time around the Earth at low Earth orbit takes about 90 minutes. So when you're outside, you're watching and you're looking at the stars, and you can do that here because we don't have a lot of light pollution. Looking at the stars and you see something, it's like, wow, that looks like it's moving. It is. That's a satellite. So let's talk about how we acquire the data. I'm only going to talk about 2 main types of acquiring data. One is a passive sensor, and one is an active sensor. So a passive sensor records the energy that naturally either radiates or is reflected by whatever it is that you're studying. So what does that mean? Well, say you're a scientist and you are reading a book. You're using the light as an energy source for your target, which is your book, and your sensor is your eye. Your brain then processes it and comes up with an idea. So this is a remote sensing. Your body is a remote sensor. You're seeing, you're hearing, you're smelling without ever touching the thing that you are seeing, hearing, and smelling. So you are a remote sensor. Congratulations, that's great. Good job. Now, we recreate that in space by having a sensor that uses the sun's light to illuminate the target, and this sensor takes the information takes it to a processing station. Does this look familiar to you? And then this scientist is sitting at her computer doing the programming, analysis, whatever that she needs to do, and then she creates the image, the application, or the information from that. So it's just like the human body, only it's much farther away. That's passive. Now an active one, and this is what we do quite a bit, an active one, if you think about, it supplies the source of energy itself. So it's not relying on the sun or the lamp or anything like that. It supplies the energy itself, and then it records it as well. So the most common one that we can think of and people know about are things like bats or dolphins, or that anybody who does echolocation, which could be a submarine, right, sends out a signal and then listens for the ping back, sound coming back, right? So we do that with the satellite with radar. So the radar satellite sends out a signal and then receives an answer back. So it's an active sensor. And the distinction becomes important when you're studying the Earth using different kinds of sensors. So one is you use the illumination of something else, and one is you provide the illumination. So how do we see the Earth? Well, first of all, this behind you right here, that is a radar image of the Okmok volcano. So this is one of the images that we take from the satellite, process it into an image that we can look at, and it looks like a black and white photo, but it's actually radar. So there could have been a cloud sitting right over that, and we wouldn't have seen it. We wouldn't have seen it because we look at this, and I want to walk you through this because I know it looks like a scary graph, but the truth is that this is really the key to radar and why we use it. So the opacity is like transparency. It's like the inverse of transparency. And the wavelength is the wavelength of the light that we see. So see the rainbow? That's the wavelength that we see with our eye. And an opacity of 100% is like a wall. You can't see through it. And an opacity of 0% is like a window. You can see through it entirely. So if we go along and we look at down here, on this axis is the wavelength. So it's the wavelength of the actual, of the light. I mean, all light is a wave. Some of it we see and some of it we don't. And it just is along a spectrum of size. So in here, this is what our eye sees. And you see that in here, how the opacity goes way down. And so we are actually able to see quite a bit. And this is the Earth's atmosphere specifically. So if you went to a different planet with a different atmosphere, you'd have a different chart. But in this one, and where we live on our Earth, visibly, we can see quite a bit through, but not all the way through. But over here, you can see that the radio waves is the length of radiation that we use in radar. And look, it's like a window. You can see all the way through it. So that's why when we say we use radar to see through clouds, that's what we're talking about. It doesn't even see the clouds. It doesn't see the clouds. It doesn't care if it's night or day because it illuminates itself. I mean, it does its own illumination. It doesn't rely on the sun to illuminate the surface. It does it itself. So this is really an important part of it. And when you think about the wavelength and the sizes that we're talking about, adult females, which I happen to be one of that group, which is great, this is about 2.5 centimeters. I know this because I measured it. So 2.5 centimeters, about an inch, right? So that, if you think about that and look at where the wavelengths are, you can start to get an idea of the size. So way down here, micro is pretty darn small. But here, it's actually big. And so it had some times, for example, there's a particular type of snow that happens, and I've only seen it one time and it was horrible because I was right in the middle of an Antarctic mapping mission and I needed to get every single piece of information out of the satellite, and it's snowing, beautiful snow. It would have made a lovely walk in the woods, but what it was about the same size as the wavelength that I was trying to talk to the satellite with, and so the radar dish is going, it couldn't lock on because the snow was the same size as the wavelength. That's bad. We don't like that. But it gives you an idea of the size and how we can see things. Now, synthetic aperture radar, this is remember I said it illuminates the ground, and then with the signal, and then something happens to it depending on the signal surface that it hits. It might scatter diffusely, which means that not very much of it will come back, right? So remember, it's measuring not only what it's sending, but what it's coming back. So not very much of it comes back. It might actually totally reflect off and none of it comes back. And then the other one, the bright signals, is it pops around a corner, and buildings are perfect for this. It'll pop it around and almost all of it will come back and it will be very, very bright. So you can discern by looking at how it's diffusing on the surface, you can discern what the natural environments are, whether it's bodies of water or if it's urban, because it will come in the different shades of gray. So it'll be either really dark, which means it's usually water, or a very smooth surface. It can be very, very bright, which is a lot of times buildings are very, very bright. And then everything else is a shade of gray. So this is what a radar image looks like. So this is a volcano in Ecuador, and a lot of what we look at is in grayscale. And people always ask me, why don't you put in color? Well, we did. After about 25 years, we started putting stuff in color. But it's naturally grayscale because of the way the satellite stores the information. So if we look at a close-up of this, we look here and we can see there's actually a lot of detail in these images, and this is all from the radar. And remember, I was talking to you about the wavelength, but there's another measurement that's important in that wave, and that's the amplitude, the height of it. And when you look at these kind of images, you're really looking at the amplitude. But there's a lot more information in radar. There's a lot more because you also can compare the wavelength from what you sent to what comes back, what it looks like, what it was today, what it was yesterday, and you can do all sorts of comparisons. And it's so much information in there. It's very complex data. That's a science joke that you'll laugh at later, but anyway. So lots of stuff we can do, which is, trust me, easy peasy, lemon squeezy. We just go do some plotting. We do a little bit of math. We throw that together. Pretty soon, boom, we have a great picture, right? There you go. No problem. And scientists have a tendency to put these kind of plots up, which and say, clearly, you can see. I swore to myself I would not say, unless I was joking, clearly you can see, like this whole night. So let me just tell you what you're looking at. So the colors are repeated bands of color that go through a scale. So if you look at when the color first appears, and then you look over at a band where it second appears, then that distance is called a fringe. And the fringe in this particular instance shows of an inflation of about 2.8 centimeters. Remember our thumbs? 2.5, right? So you get about that much change. So this is seen from space. You can see differences on the order of centimeters. So sometimes the difference is in time, and sometimes the difference is in space. That's the tricky bit that we're not going to go into much here today. But if you have deformation, so in this case it's a volcano, it's kind of hard to see up here. These are actually lovely images. But do you see how it looks like rings? Like the pink really stands out, right? You can just see how the pink repeats itself. So every time There, the pink goes to the next one, it's 2.8 centimeters. And so that could be for deflation, it could be going in, subsidence, or it could be inflation. And look at this, do you see how there's no real pattern to the color? If there's no real pattern to the color, you know that there's no deformation. So that's how we do. Actually, Dr. Jens in the back spends a lot of time looking at these tie-dye plats. So you can take the fringes and demark them, start calculating the distance, and you can get measurements on at the centimeter level of mountains taken from space. And so remember that image I showed you before? It's actually the interferogram of this area right here. So you can see that in this case, it's showing the elevation. So remember, I told you that the fringes can show you changes in time or changes in space. And we can also mix passive and active data together. In this case, you have as a base underneath it, this is from Google Earth, and this is a visual, it's a passive sensor taken information. Over the top of it is an interferogram that was taken from the radar satellite, and the information was two different two different acquisitions in time, and it was before and after the Kathmandu earthquake. And there's the epicenter. I don't know if you can see it, but those are the fringes from the earthquake that you can see. So you can measure the deformation of the earthquake before and after using the radar satellite. It's cool stuff, right? Yeah. So another thing that you can do with these interferograms is you can create digital elevation models. And digital elevation models are the things that are the base maps that are underneath the information that tells us about how about maps. And for Alaska, this is really, really a touchy subject because we're one of the last states to have really old, inaccurate maps. We have such a huge space, it's very expensive to map it, especially using the traditional methods. But if you use the satellite imagery, you can get a lot of data fast, and it's a little bit easier. So this is an example of a flyby that's created. So that's the photo of the volcano, and that's the flyby that was created using radar data. So now I'm going to show you some more just examples, different perspectives. So this is Mount St. Helens. These are both passive sensor images. This is a Landsat image here, and this is a photograph taken from an airplane. So you can immediately see that in the airplane, you get a lot more detail. First of all, I hope this is unmanned. I think it wasn't. I think this was actually a manned craft. But pretty close to that eruption. You can get a lot more detail, but you don't get very much area, whereas with the satellite imagery, you get less detail, but more area. So again, it depends on what you're looking for. And then I thought for fun, we should look at some Fairbanks images. So this is the university in 1938. So we have these all at the Geophysical Institute, these old photos. It's kind of fun. In this one, I spent an embarrassing, I should say, amount of time staring at this photo going, what? What? So it's 1949, and this is, you can see, like when you're not looking on this kind of a screen, that that's an airport, and I just had the hardest time figuring it out. I'm like, what is the airport doing there? And you look up close and you can see that this is part of the railroad. And this little smudge on the hill is the university. Okay, so I had to think about it. 1949. This construction site, yeah. In 1951, that became the airport. This is weeks. Yeah, it's weeks. It's weeks. Well, and I was going, well, wait a second. It's on the wrong side of the river to be Phillipsfield, but then, yeah, it's weeks. That's what it is. But man, life before Fairbanks International. There you go. But we have a lot of these aerial photos, and these again, these are the passive sensors. So when it's passive like this, you'll see clouds, right? You'll see cloud interruptions. So you can go through and take a bunch of photos and have them not really work for your study because you can't see what you're trying to look at, unless you're trying to look at the clouds, in which case they're perfect. But so we have a lot of these images, and you can do a lot of studies about the urban changes that happen using satellites. But now we look at it from space, and this is actually a radar image. It's confusing that it's radar because it's color, but this is multiple phases, and what we do is we take the different bands, and we put one in as red, one in as green, and one in as blue. This is one of our favorite tricks. We love doing that. And you come up with the color image that's radar. This one, and I think actually, Rudy, did you make this one? Yeah, me neither. No. Anyway, so this is the Bering Strait, and this is what it would normally, this is what it looks like in radar on this side. And so this you see Alaska here, the Bering Strait, lots of sea ice. But if you want to really look at the detail, you need to figure out a method of really pulling the detail out. So in this one, what they did was they took I really suspect it was Rudy, but there's 3 images. One is from November of 2017, one's December 2007, November 2007, December 2007, and then January of 2008. So one image, each like every month for 3 months. We put one image in as red, one image in as green, and one image in as blue. So you get all this color here where it's not the same in each image, but you get gray tone where it is exactly the same. So the land didn't change, but the water changed and the sea ice changed. So you can look at what changed when by looking at the color and the mixes of color that happens. And it's beautiful. So art, science, same thing. But you can get a lot of information by doing that. We love the whole RGB trick. It's a great trick. So Anchorage, turns out, is beautiful from space. Who knew? And this is Anchorage right here. And you can see so much detail in this Sentinel-1 image. It's amazing. And I've actually, in order to put it on a slide, I had to compress it down so it's lost a lot of its information. But this is all radar, and you can see the tide has gone out, so you can see some of the silt and the wind-blown water. And I don't know if you can see it. Do you see these dots out here? Yeah. Those are the oil platforms that out there. You can see the delta, all sorts of detail. The green comes, whoops, oh, I did it again. Okay. I get excited, I start pushing buttons. Let's try this better. So there's just so much detail in the radar. You can spend a lot of time just in one area. And I call this the southern suburb of Anchorage. So this is the big island of Oahu. And we did the same thing with this, with the red, green, blue. So we can see the different aspects of it. This next one is one of my favorites. Absolutely gorgeous. So this is in the Namib Desert in Africa, and these are rock outcroppings. And what you see here are the waves in the sand that's caused by the wind. So it's in the radar, you can look right through whatever it is that's causing the problem, but you see these huge structures of that are basically, if you think about winds on the water, it's that this is winds on the sand, and the outcroppings have changed the shape of the sand. It's beautiful. So I'm going to show you 2 different views of the Alaska Peninsula. It's Katmai National Park. So this is the radar image that is taken. Like I said, there's lots of information in here. But if we take it and we work with it a little bit, you can start pulling out the information. And this is the same area, slightly different time, but then we've taken it and added some information to it. This image, and this is actually on the calendar. It's in the calendar. We were publishing the calendar just before a big science meeting in December, and we picked out an image for the front cover. And just before we went to print, we got some data from Irma, and we switched it out, and we said, no, we got to show this. This is amazing. So this is the surface of the ocean. This is a radar image of the surface of the ocean. And what you're seeing is the imprint of the hurricane force winds that are on the ocean. And you're seeing the change in the ocean surface. You're not seeing the hurricane itself. You're seeing the effect of the hurricane. So it's pretty amazing. So we've had a few of these in the past where we've been able to see them in the radar at the surface of the water. And then we see from different satellites, we see the actual hurricane clouds and wind itself, and you can put them together. So this is the radar image, and this is it's kind of mind-blowing. I love it. So this, I'm going to show you a little movie. This is Las Vegas. So it starts in 1984, and I want you to watch two things. The change that happens in the city of Las Vegas and the related change that happens to the water reservoir. Let's see if I can get this one to work. Yeah, there we go. Is it working? Do you see it? So watch the city, watch the water. So human civilizations need water. The Hoover Dam was built to help Las Vegas. But as you notice what happens, as the city grows, the water depletes. So this is a pretty natural phenomenon. Now, this urban sprawl, as they say, is not really above average in terms of its speed or its size. It's from 84 to 2016. This is about what you expect in the United States for cities growing. So, but in this particular movie, you can really see it because of the radar characteristics and the way the Las Vegas shows up. But I think it's a fascinating, and this one you can find out there on the net. So what's up there? So 1957, what happened in 1957? Sputnik. Sputnik went up, and I just thought I would mention that the Geophysical Institute scientists were the first people who heard it. Just saying. But look at this was just a couple years ago. This is what our space looks like. There are so many satellites up there, and most of the satellites that we send up there, they stay up there. And we have to not run into them with our satellites that we have now. And we are putting more up, and we're now, the satellites are getting smaller, so if they're smaller, we can put up more, right? So the space is pretty crowded up there. So that's kind of what it looks like now. So I'm hoping that what I presented to you tonight makes sense and that you are interested. So from my perspective, there's so much going on up on the hill. We have a lot of scientists, a lot of engineers, a lot of mathematicians, all hard at work, working on the science. A lot of them are looking at remote sensing, but I'm just going to say that I think science has the best toys. Thank you very much.